In today's lesson, we're going to be talking about synthetic division. So what I have here to the left-hand side is I have a illustration of dividing polynomials using long division. And we saw here for a given polynomial, in this example, this was a degree 3 polynomial. We're dividing that polynomial by x plus 1. That's our divisor. And we found that we resulted in a quotient of x squared plus x minus 1, and this was our remainder down here. So we saw that the process of dividing polynomials using long division was a bit tedious at times, and thankfully, when you have a divisor that is linear, i.e. a divisor of degree 1, you have a bit of relief and a more efficient way of dividing these polynomials out using synthetic division. So let's take a look at tackling this problem here using synthetic division. Step number 1 is you identify your divisor. In this case, the divisor is x plus 1. We're going to go ahead and find the root of your divisor. So the root of my divisor is -1, so I write that down. So now what we're going to do is we're going to identify our polynomial. It's our degree 3 polynomial. We're going to copy the coefficients of the polynomial down in descending order by degree. So we have x cubed has a coefficient of 1, 2x squared has a coefficient of 2, and then there's no x variable there, so it must be a 0 in front. Don't forget to do that. That's important. And then lastly, the constant term of -5. Once we have this written down, we go to our first column. We're going to drop down that number. In this case, the number is a 1, so we drop that down. Now what we're going to do is we're going to go ahead and take 1 multiplied by 1, which is -1, and write it in the second column. Adding the numbers in the second column, we end up getting 1. Continuing on with multiplication, 1 times -1 yields -1. That goes in the third column. Adding up the numbers in the third column, we get -1. Then we have -1 times -1 is +1. Adding this up, we get -4. So now that we've gone through the process of the synthetic division, we want to be able to interpret our table here. So I've highlighted some key characteristics of each table. You'll notice here we have x plus 1, which corresponds to the root of -1. We have here -4, which is your remainder, which is also your remainder for synthetic division. It turns out that the last column using synthetic division will always represent your remainder. The question becomes is how are these two connected? Well, we had a degree 3 polynomial and we divided out a degree 1 polynomial. We are then left with a degree 2 polynomial, as we saw here. These are the coefficients of our degree 2 polynomial. So in this case here, this relates to 1x squared plus 1x minus 1. So therefore, we have a direct connection between the work we did with long division of polynomials and our synthetic division approach. Let's take a look at some more examples using synthetic division. So for this example here, using synthetic division, we want to determine whether x plus 2 is a factor of our polynomial. Well, to be a factor of the polynomial, you must have a remainder equal to 0. So let's see using synthetic division if we have that. Again, the root of x plus 2 is -2, so we put that down. We write down the coefficients of our polynomial. Then first number gets dropped down. We're going to use addition here, and we're going to go 1 times -2 is -2. Adding, we get 2. 2 times 2 is -4. Adding, we get 0. So like we had identified earlier, this last column represents our remainder. Since the remainder is 0, that means that x plus 2 is in fact a factor. You can see this more clearly using the division algorithm. You'll notice here, using the division algorithm, our polynomial is equal to our quotient times our divisor plus our remainder. And by doing so here, essentially, we have a +0, which we can just erase and represent as this here. And now we have here that x plus 2 is in fact a factor of the polynomial. Let's take a look at another example. In the next example here, we want to find the remainder when x squared plus 3x plus 1 is divided by x plus 4. So let's go ahead and do that. Using synthetic division, we find the root, which is -4. Draw our line here, and then we have a coefficient of 1, coefficient of 3, and coefficient of 1. Going through the synthetic process, you'll see here going through the synthetic process, we get a remainder of 5. Now, using synthetic division, we can see how quickly this is. Let's take a look at doing this using long division. So again, doing this using long division, we'll see that we also get a remainder of 5. Now, the process for long division can be more tedious, prone to more error, but when you do have linear divisors, it is useful to use synthetic division as your method. But just to show you both ways, we can go ahead and get an answer to this question, one using long division, the other using synthetic division. Let's take a look at some more examples. Using synthetic division here, we want to determine whether x minus 2 is a factor of x cubed minus 8. So once again here, we find the root of our divisor, which is 2, and we write down the coefficients of our polynomial. In this case, it'll be 1. Notice here there's not an x squared term or an x term, so I have to put zeros in that location. Again, you drop down the number in the first column. Multiplying, we get 2. Adding, we get 2. Multiplying, we get 4. Adding, we get 4. And lastly, we get 8. Again, giving us a remainder equal to 0. So right away, I know that x cubed minus 8 must equal my quotient. So we're dividing a polynomial of degree 3 by a polynomial of degree 1. So you're going to go ahead and reduce this by a degree. So this is going to be 1x squared plus 2x plus 4 as our quotient. And then we have our divisor here is going to be times x minus 2. So notice here we can see that because we have a remainder of 0, we could say that x minus 2 is a factor of x cubed minus 8. Furthermore, although the question didn't ask it, x squared plus 2x plus 4 would also be viewed as a factor of x cubed minus 8. Let's take a look at another example. For the next example here, we want to determine, is x minus 3 halves a factor of 4x squared plus 9? Well, again, the same idea. You find the root of your divisor, which is 3 halves, write down your coefficients here, and then we go through the synthetic division process. So going through the synthetic division process, the remainder becomes 18 here. Again, how I got that, you always drop down the 4. 4 times 3 halves is 6. Adding, we get 6. Then 6 times 3 halves is 9. And adding, we get a remainder of 18. So our remainder here is not equal to 0. So therefore, x minus 3 halves is not a factor of 4x squared plus 9. Let's take a look at this using the division algorithm. And you can see here, using our division algorithm, we get 4x squared plus 9 is equal to our divisor times our quotient plus remainder. And again, that quotient is going to be 1 degree less than our polynomial, so it would be a degree 1. So this must be 4x plus 6. Let's take a look at another example. For the next example here, they give us a degree 5 polynomial, and we wanted to determine whether p plus 3 is a factor. So once again, go through the process of synthetic division. When we do this, we get, and doing this here, we can see here we end up getting a remainder of 0. So it is true, p plus 3 is a factor of our polynomial. When we do this using the division algorithm, we'll see that our polynomial is equal to our divisor times our quotient. And again here, this was a degree 5 polynomial, so this becomes a degree 4. And you'll see here this becomes 1 p to the power of 4 minus 3p cubed minus 4p squared plus 12p plus 0, which I didn't write. And then we have a remainder of plus 0 written down as well. So right away, you might notice that we can do more with the polynomial. Now, the question's answered at this point here, but there's more to explore with this question, so we might as well look at it. You can take a look here. We have a factor of p that can be factored out of the polynomial, so let's go ahead and do that. So I factor the p out of the polynomial here. You'll notice here now we're left with a degree 3 polynomial inside. Now at this point here, if you wanted to find more factors, like right now we've just shown, okay, p plus 3 is a factor of a polynomial, and based on this decomposition, we now know that p is also a factor of this polynomial. We want to know, are there any more factors to explore? What we can do is, instead of doing synthetic division again on this expression and trying more numbers and seeing which ones will yield the remainder of 0, we could do synthetic division on the cubic polynomial here. So let's go ahead and do that. Doing synthetic division on the cubic polynomial, I tried -2, and using synthetic division, I got a remainder of 0. So therefore, p plus 2 is also a factor. Let's take a look at what we're left with. Continuing on here, now we know that p is a factor, p plus 3 is a factor, p plus 2 is a factor, and this is our quotient left over from before. Right away, you can see here we're left with a simple trinomial. That'll factor easy, so we have p is a factor, p plus 3 is a factor, p plus 2 is a factor, and now our quotient factors into p minus 3 being a factor and p minus 2 also being a factor. So we can see here that our degree 5 polynomial has 5 factors: p, p plus 3, p plus 2, p minus 3, and p minus 2. Again, doing synthetic division on 0, -3, -2, 3, or 2 will each yield a remainder of 0. Let's take a look at another example. For the next example here, they want us to find the value of k such that the polynomial, which has a coefficient of k that we don't know, has x plus 2 as a factor. So they've kind of switched it on us. We know that x plus 2 is a factor, and now we want to find the value of k, the coefficient in front of that x squared term that's going to make this polynomial a factor. Well, if this polynomial is a factor, then using synthetic division, we have to have a remainder of 0 when we're done. So again, just to remind you, synthetic division only works when you have linear factors. So I'm going to go ahead and write down the coefficients of my polynomial. So I wrote those down, and again, we have that k now along for the ride in the synthetic division. So 2 times negative 2 is negative 4. Adding, I get k minus 4 this time. And now you're going to take k minus 4 times negative 2 is negative 2k plus 8. And then we're going to add the column here, and in which case we get negative 2k plus 1. And then we're going to take negative 2k plus 1 times negative 2, giving us 4k minus 2. Adding this up, we get a remainder of 4k plus 4. Again, this is our remainder when the coefficient is k. We want this to be 0 because we want to have x plus 2 as a factor, so our remainder must equal 0, in which case 4k plus 4 must equal 0, which implies that k equals negative 1. So therefore, when k equals negative 1, this polynomial will have x plus 2 as a factor. All right, that concludes our lesson on synthetic division.